Okay, so welcome back. In this video, we're just gonna keep deriving the distribution of our alpha hat. So previously, we know that the alpha hat equals to y bar minus beta hat times x bar. And also remember, in the last video, I mentioned that if we know a variable which goes to normal distribution, and that variable times a constant plus another constant, that new thing will also goes to normal distribution. So accordingly, we find that the beta hat, we already know that beta hat goes to normal distribution. And this x bar is a constant, and the y bar is also a constant. So that's also going to fit into that pattern. So we know that this alpha hat also going to goes to a sort of normal distribution. Okay, so now we're going to go on and find out the mean and variance of alpha hat. So let's do this. So the mean of alpha hat is actually the expectation of alpha hat. Remember, so we have expectation of y bar minus beta hat times x bar. And also here, remember, also in the previous video, we know that y bar is going to be equal to alpha hat plus beta hat. I'm sorry, not alpha hat. Let me cross this out. So it's going to be equal to alpha plus beta times x bar plus mu bar. Okay, so let's substitute this expression into the expectation. Then we have expectation of alpha plus beta times x bar minus beta hat times x bar plus mu hat. Okay, let's break it down a bit one by one. So the expectation of alpha, this actually just going to become the alpha itself, right? So because alpha is constant. And plus the expectation of beta times x bar. This beta is also constant, x bar is constant, so this term will also equal to itself. And the third term, we have expectation of beta hat times x bar. So the x bar is constant, we can ignore it. So the beta hat, expectation of beta hat, and in previous video we also know that it also become equal to beta times x bar. So these two terms just going to be cancelled out. So finally we have expectation of mu bar. So we just write in the sum form, which is 1 over n times the sum of mu I. Then in the OLS assumption, we know that the expectation of mu I for each individual mu I, it must be equal to 0. So now the fourth term also going to be equal to 0. Okay. So now we know that the expectation of our alpha hat is just going to be equal to alpha. Cool, no problem. And next, we're going to find the variance of alpha hat. So we're just going to keep writing alpha hat in this form. So the variance of alpha plus beta times x bar minus beta hat times x bar plus mu bar. Okay, so actually I finished the whole video and just realized my microphone is out of battery, so now I have to go back and do this all over again. But anyway, now what we need to find out is the variance of this whole term. So let's break them down one by one. So the variance of alpha is the variance of a constant, and that will goes to 0. And the same goes to the second term, because the beta and x bar are also constant, and that also going to disappears. So what we're going to be left is a variance of minus beta hat times x bar plus mu bar. So in the previous video, we know that the variance of a plus b just going to be equal to the variance of a plus the variance of b, and plus 2 times the covariance of a and b. Okay, so let's now let me write it down here. Let's see what each term is going to be equal to. So the first term, variance of minus beta times x bar. So here the minus x bar will comes out and becomes x bar squared. So it's become variance of beta hat. And in the last video, we know that the variance of the beta hat is just going to be equal to the sigma square over the sum of xi minus x bar take square. Okay, this is what we learned in the last video. So for the second term, so we're going to write the mu bar in the sum form, which is variance of 1 over n times sum of mu I. So in the same manner, like the 1 over n comes out and becomes 1 over n squared, and it's actually the sum of variance of mu I. So this term actually going to becomes 1 over n times sigma square, and this n will be cancelled out with the square. Okay, cool. So for our third term, the 2 times the covariance of the minus beta hat times mu I and mu bar. So what is that term? So to find out, we have to go back and look at the definition of covariance. So actually covariance, let me write it down here. The covariance of A and B just going to be equal to the expectation of A and B minus the expectation of A times the expectation of B. So just use the same pattern. We know that the covariance of minus beta hat x bar and mu bar is just going to be equal to the expectation. Let me write it down here. Just going to be the expectation of minus beta hat times x bar times mu bar, and minus expectation of this term and the expectation of mu bar. And we also know that the expectation of mu bar, this term is equal to 0. So the second term just going to be disappeared. So now the whole problem becomes, what is the expectation of minus beta hat times x bar times mu bar? But here, like, the beta hat is a variable and our mu bar is also a variable. So it's kind of hard to dealing with. But remember, in the previous video, we learned that the beta hat is also equal to, actually, let me write it down here. This beta hat is equal to beta plus the sum of xi minus x bar times mu I divided by the sum of xi minus x bar square. So now let's try to substitute the beta hat with this expression, so that the only variable that's going to be left is going to be mu, or sort of mu bar or mu I. So let's just do this. The expectation of beta, actually we take the minus sign out, so we just only have beta hat inside the parentheses. That's going to be more easier to looking at. So the beta plus this whole thing, let me write it for real quick. Okay, and the xi. Actually, let me use the square brackets. And the whole thing's times x bar times mu bar. Okay, cool. So because x bar is also a constant, so let's take it out as well. It's just going to become, and we times the mu bar inside the parentheses, we have beta times mu bar plus this whole term times mu bar. Okay, again, if we expand the expectation sign, then we have the expectation of the first term plus the expectation of the second term. But also, the expectation of the first term is something times mu bar. And expectation of mu bar is going to be equal to 0. So the first term also disappears. So what we're only going to be left is the expectation of the second term. Okay, now here let me write the mu bar in the sum form, which is 1 over n and the sum of mu I. So now we have, okay, actually before we do that, let's just factor out, let's just take out some constant as well, because now the 1 over n is a constant, and the denominator for this term is also a constant. So let's just take them out, and it's become the expectation of this whole term times the sum of mu I. And this looks much better. Okay. And now we have a sum times another sum. So if we would like to expand the parentheses, that's going to become some expectation of a long polynomial. So at the first glance, you might have no idea how to dealing with that. So how about let's assume, or actually let me write down the prefix, the suffix, I'm sorry. So this is going to be I equal to 1, this is going to be j equal to 1, and n, okay. Because it's a two different sum, so we have to, specify the suffix. So let's assume that we have only two instances. So if I have no idea how to dealing with it, just write it down, just term by term. So it's just going to become, let's see, let me write it down here. So it's going to become x1 minus x bar. I'm sorry, so x1 minus x bar times mu I plus a mu1, sorry, x2 minus x bar times mu2, and the whole sum times mu1 plus mu2. Okay, and let's expand this expression, see what kind of pattern we can find. So the first term times the first term is we're going to have, okay, so x1 minus x bar times mu1 square. And the first term times the second term, we have x1 minus x bar times mu1, mu2. And the second term times the first term, we have x2 minus x1 times mu2 times mu1. And also plus the second term times also the second term. That's become x2 minus x bar mu2 square. So if we would go ahead and take expectation of the whole things, and that's going to become the expectation of the first term. Okay, that's just going to become x1 minus x bar, and the expectation of mu1 square. Well, based on the OLS assumption, we're going to have the sigma square. Okay, so the expectation of the second term is going to become the expectation of this term, this strange-looking guys right over here. So what is the expectation of mu1 and mu2? Well, also based on the LLS assumption, we know that mu i's are identically, well, independent distributed. In other words, the expectation of mu1 and mu2 should be equal to 0. Then this whole term, if we take expectation, this whole term just going to be cancelled out. And in the same way, also going to be applied for the third term, because the mu2 and mu1 is also independent with each other. So if we take expectation, this third term will also goes to 0. And if we take the expectation of the fourth term, we know that the expectation of mu2 squared is also going to be x2 minus x1 sigma square. So now we kind of find out the pattern, which is whenever the I and j is not equal to each other, then after we apply the expectation, that whole term disappears. So now this whole thing we can just simplify it as, okay, let me write it here. Okay, let me write it in this page. So the whole things we can actually simplify it as I and j. This thing's it's just going to be equal to, well, based on the pattern we find, just going to be the sum of xi minus x bar times sigma square. Okay, so this is what we have, and remember the sum of xi and minus x bar is just going to be equal to the sum of xi minus n times x bar and times sigma square. And these two terms are exactly the same, so this whole term just going to be equal to 0. So now that we understand the expectation, okay, this term just going to equal to 0, so that this whole thing, I mean the covariance of the minus beta hat times x bar times mu bar is just going to be equal to 0. So actually the variance of our alpha hat, okay, it's just going to be equal to this term plus this term. Okay, let me write it down at the very beginning. Okay, plus sigma square over n. So this is the variance of alpha hat, and also we have the mean of the alpha hat equal to just equal to alpha. So now we know that the alpha hat actually goes to a normal distribution with the mean of alpha and the variance of this term. Okay, thank you. I will see you in the next video.